right, so let's do temperatures. And we'll talk about safe limits because I like that. And then we'll talk about typical risk controls. And then we'll just look at a test plan again because of that whole temperature test thing and abnormal temperatures. All right, so table 22 is the safe temperatures of internal parts, normal condition. And so that's effectively safe limits. And it gets into the magnetics, so transformers, motors, those all have safety critical insulation if the motor's in a dangerous voltage. Transformer, same criteria, but it'd be more commonly. You know, it used to be all the motors were in mains. Now we see all the motors in, 48 volts or less. Less than the 60 volt operator limit. But anyway, we have limits. By default, all insulations considered class A, and there's a limit of 105, but that's in a 40 ambient, or whatever your ambient is, if it's higher, the max. And so that rise is 65, I think. Yeah. And if you had insulation classes that are higher, and what happens is those vendors evaluate the materials together for that. There's an IEC 85 as well as a UL standard. So by default, you want to comply with at least the 85. And so sometimes you can be class B, F, or H. H is very high stuff, like Nomex and Teflons. So parts have their own ratings and they become the limit. Boards and wiring have their limits, or if they don't, there's some generic limits. Parts in contact with flammable liquid with a flash point. So you'd want the temperatures to stay at, not just under the limit, but 25 under the limit. And then wood's allowed to be 90, like we use wood a lot. That's an oldie but goodie. So when we check temperatures on magnetic, motors and transformers, we check it with a thermocouple, which is how we normally check temperatures. We have to be actually 10 degrees C less than the limit, because thermocouples are checking the outside surface temperature of the transformer inside the enclosure, but on the outside of the transformer, and inside could be hotter. And so with resistance methods, we get an average, and the limit applies for change in resistance. So if you're copper or aluminum, say copper, we know its conductivity, and if we knew the resistance cold and hot, we actually know that temperature rise. And so there's a formula. But we generally just use thermocouples, and so we have to be 10 under the limit because we're lazy. All right, and then there's surface safe temperatures, internal part, false. Okay, so we're still talking about transformers and capacitors and things. But in single fault, this is the motor transformer stuff. And so we can be hotter because presumably it's less time. This single fault probably resulted in a fail-safe, a stoppage, although not necessarily, it could be impedance protected. Anyway, these temperatures are allowed. All right, and then moving on to surface temperatures, table 23 and 24, we kind of took a peek at. Here's your 23 for operators, and depending on time, we can be a certain temperature. How much heat comes off of a surface material can vary. Metal conducts very quickly, plastics less quickly. So we actually allow higher temperatures for slowly, less thermally conductive materials. Metals don't forgive. So if you pulled away too slowly, the metal will have injured you, whereas with a plastic, you'd have the opportunity to pull away slower because you wouldn't have experienced the full heat until a few more seconds. So, so these time limits again look great, right? That, oh yeah, I love black and white, you know, this time, this temperature. But how do you know the time? You don't. So, you know, operator controls are going to be touched maybe longer, or at least necessarily so, than a surface that doesn't need to be touched for control. And so a surface that doesn't need to be touched for its intended use by operators, say, you can use these shorter times because he can untouch it. But when he has to touch it to fulfill its intended use, then we have these ideas where it's going to be longer. But how long? So, in fact, it's considered a risk management result in the test report form, the CB test report, that the various controls are specified as falling into whatever time period and whatever limit. And we're supposed to identify that the manufacturer has done that in the test report. Either the manufacturer filling out his own report or if he hired a test lab. So the test lab will ask you for that risk management result. All right, and then these you know, if you have higher surface areas or whatever, you need to think about these things being maybe different. Safe temperatures in single fault on a surface. This is new. This is Amendment 2. So if you're up to Amendment 1, 2012, which is what we're using now, this table doesn't exist, and you have to meet this table, although there is some kind of a guidance, what do they call them? Interpretation sheet, and this is an IEC interpretation sheet that says, I don't know, 105 if your risk management allows it. And then this says less than that. So in some ways, Amendment 2 restricts that interpretation sheet. But maybe that interpretation sheet wouldn't be as relevant for as many situations. So then Amendment 2 is friendlier. In any case, this was needed, and we got it into the Amendment 2. And so we do allow surface temperatures to be hotter than we'd normally like, but it's because we're in a single fault condition. And hopefully that's somewhat detectable. But now these are operator surfaces. So if it's an applied part, we wouldn't have this. Applied parts have to meet temperature limits in normal and single fault. So if you think about an ultrasound transducer, if you do a fault where one of those transducer doesn't shut off, it would be a bit warmer. And that's got to stay within the normal limit because it's the applied part. You know, all those transducers multiplex. All right. Here's patient limits for an applied part or pseudo applied parts, right? So both. And here's time and temperature for various materials. And again, how do we interpret these times? Sometimes it's not as obvious as we'd like. Sometimes it is. I mean, this is the clinical function. How long does that have to be applied? You know, sometimes we might know. So, so again, that's all risk management results, actually. The test lab's not supposed to figure this out. The manufacturer is. All right, so thermocouples are two dissimilar metals, and when they see a temperature, they have a voltage, and then that's very accurate. There's a curve. It's not linear, but it's almost linear. And so we can pretty accurately know the temperature, and it's completely, you know, material science related. So it's something that's calibrated because of the purity of the materials. And we apply thermocouples according to CB guidance, whatever it is. There's a interpretation sheet with super glue. Is it, what's the chemical? Whatever, like super glue. So what happens is if you apply it with super glue and you rip it off, the bead breaks, and then you have to re-weld them or buy new ones every time you test a product. So that's all well and good if they're very hot. This tape wouldn't be very good because it'd be too loose. But this is 130 tape and it's a glass cloth, so it's the higher temperature tapes. And so in practice, you'll see we do apply thermocouples with these high temperature tapes. But if the temperature gets anywhere near 130, which is what the tapes are rated for, you'll see, and because you check the temperature every 15 or 10 minutes, you'll see the temperature maybe, be very hot, and then all of a sudden it's less hot. And it's because the tape got loose. So, and you also can you're monitoring the absolute temperature as well. So you have to keep in mind that there's limitations to this method. But generally you're way under the limits for the tape. And so it's a very effective way to apply thermocouples. And you can quote me on that. But it's not in the CB guidance. Anyway, this is an example of some boards and power supplies with thermocouples, right? Yeah, here's the endoscope, which gets all nice and hot. Here's a blocked ventilation opening, so that's an abnormal condition with the higher limits. This is a temperature, well, it's a data logger in general. You could log voltage, current, resistance, but they're very common for the temperature capability. In effect, you're measuring voltages, but it reads out in temperature. There's multiplexed cartridges that go in the back. These hold 40 or 20 thermocouples, depending on whether you want them to float. And so you hook up a lot of thermocouples in here, and all those little channels get multiplexed by the meter. And the meter can log it. There's a port in the back. You can export it to your laptop, or you can cycle manually through here each channel over time. So that's how we do temperatures. Okay. So in general, if you had a heater, you want to think about single fault safe. So we call the first one the regulating temperature device. And then if that should fail, we're looking for a limiting device. Obviously, not obviously, but I want to mention that detectability would be nice there. So you should have a manually reset limiting device. And then to protect against surface temperatures, adequate enclosure ventilation. So sometimes you might need a fan or whatever ventilation you're trying to do. And in any case, the need here is to meet your temperature limits. And then there's ways to, by inherent design risk controls, you can do that, or whatever they're called. The risk control strategy that's recommended first. All right, so a test plan. Here's my input test because that prevents fire. There's a capacitor discharge test. When you unplug a product and touch the pins right away, that needs to discharge. So nobody gets a shock within 1 second or 10 seconds in some cases. So that's shock related. Then a temperature test. So we kind of knew about input and temperature, but I've added the cap discharge, leakage, dielectric, before and after humidity we talked about. But then we get to do fault testing. And so there's single fault tests on components, any pin to pin, open or short. There's overheating of transformers. There's impairment of cooling, blocked vent. There's locking of moving parts. There's overload of heating elements, exceed duty cycle. So this is all the exciting stuff. And leakage dielectric after all that exciting stuff. Yeah. All right, so that's thermal. And in 5 minutes, we'll cover fire and oxygen rich. I shouldn't laugh. I think actually you'll absorb the content in that time, so we're okay. All right, so safe limits. I would consider the 15 watt after a minute to be like an inherently safe. There can't be a fire. There's no ignition source, if you will. So I'll mention that in the safe limit kind of area that I'd normally talk about. The other thing is this 25 less than the flash point for flammable liquids. That's sort of a safe limit as well. Um, but the concept we'll continuously try to understand is you need fuel, you need an ignition source, you need oxygen, and you're going to have a fire. And so with safe limits, we're trying to remove the ignition source. Okay. So otherwise, we might have an ignition source, and so what should we do? And there's three strategies. There's a construction strategy where we talk about a fire enclosure to contain the fire, and there's flammability ratings for the fuel inside the fire enclosure, as well as a flame rating for the fire enclosure. And there's a testing approach. Yeah, I don't know if you have too much fuel or lack of containment. But what we'll do is we'll do a whole bunch of great tests to try to have a fire. And if there's no fire, I guess you had an appropriate level of fuel and good containment. Yeah. And then there's something in between. And that's to kind of control our fuel, but also our power, not to 15 watts, but will allow 100 watts. Okay. All right. And so when we take the construction approach, here's our fuel. Our wire has to be V2 according to the newest amendment. And then with the current Amendment 1, there's some Annex A rationale for justifying V2, but it's explicitly required, allowed in the amendment. And then connectors and boards have to be V2. So we're taking care of fuel. And then on the enclosure side, we need bottom openings to be very, very, very small because flammable particles fall. And then sometimes we consider the side to be the bottom if you're within 5 degrees. And then otherwise, the material of the enclosure is supposed to be metal except magnesium. And if it's plastic, it needs to be V2 if it's transportable or V1 if it's stationary. And if you don't know what V2, V1, V0, 5V, and HB is, HB is very bad. It burns about as well as a cigarette. And then there's a big gap. V2 is bad, but much better than HB. These are vertical burns. This is a horizontal burn. This is self-extinguishing and doesn't burn very much at all. And then there's a big gap where 5V is a bigger flame, more energy, and it's a panel, and it's self-extinguishing. So 5V is very good, and I would say there's a bit of a gap between V0 and 5V in terms of much better. And this is a big gap in terms of much worse. And so we saw V2 mentioned a lot. And so when we need at least V2, we'd take any of these, okay? And we wouldn't take this. If V1 was our limit, we couldn't take the V2 or the HB, yeah? Is the side the bottom? Well, if you're within 5 degrees, so things fall vertically, but, the equipment could be tipped or for whatever reason, it didn't quite fall vertically. That becomes the bottom as far as restricting the size of openings. So keep that in mind. All right. And so if we take a construction approach, we admit there's ignition, we admit that there's the oxygen, but we've limited the fuel, and then this green box is the containment. And so we think the risk of fire is quite low. With the hybrid approach, we've limited the ignition a bit to 100 VA. We've limited the fuel a bit, no containment, but we think there's no risk of fire. So we're doing lots of tests. So there's that whole test approach. And so if you take the fire enclosure and the hybrid approach, theoretically, you don't have to do these tests. On the other hand, if you do these tests and it resulted in shock, then you should do them because you still need to show adequate risk control for shock. And I know it's 5 o'clock, so I apologize, but we are almost done. And so if you did think you don't have to do it for fire, that's true, but you do need to do it if you think it could result in shock or whatever. Okay. But in any case, the other thing is fusing's nice. So in fact, the standard requires fusing for short circuit protection. And so we sort of saw in the mains that pop thing and for ground faults and short circuits. And so that's the 811.5 that talks about that. The thing I'd mention is this high breaking capacity. There's a 1500 amp rating on H fuses. These are IEC fuses. And so if you're in the mains, you have to have an H rating, so be careful. With batteries, a similar situation. We've got some joules, and so we should have some fusing. So we're allowed to have a distance of 2 means of operator protection for the voltage. And if we meet that distance, we don't need a fuse. And once we have a fuse, we don't have a distance requirement. We can accept the possibility of a short. And so sort of this is to show that there won't be a short, if you get me. And you'll find that in the 815.4.3 battery stuff. Here's all your battery chemistries and component standards. Certainly lithium rechargeable. So secondary and primary for batteries means chargeable or not. And so if you have a chargeable lithium, it's very exciting, and you need these good standards and the single fault safe smart charge for discharge as well as charge. Coin cells have kind of their own thing. This is an example of a smart charge. It comes with the battery, but only the battery got certified to the ratings that this limits it to, discharge and overcharge. So this still needs to be evaluated as single fault safe in the end use. And you generally get a theory of operation on that card. A resistor and a diode will generally prevent charge on a coin cell, and so you have to do that. There's also chips that do this, but they're certified for that. These batteries don't need anything. They're generally inherently safe. All right, and then think about, operator service and usability issues about reverse polarity and child swallowing lithium batteries. So there's a lot of children in the emergency rooms from swallowing batteries. So, all right. Last, these metallized parts, this could flake off. And so the US and Canada have a component standard to show that that doesn't delaminate, flake off, and cause fire or shock. And so you would need to, if you're selling in those markets, have that certification. And it's something where the plastics and the paint have to be evaluated together. So that's all coordinated from your vendors. All right, and so that's sort of it. Last but not least, oxygen rich. The idea is if you go over 25%, things will burn better. And so once they burn better, ideally we'd want to limit the ignition source. So there's some curves, figures 35 through 37, that talk about energy that we could limit things to. And these are the ranges. depending on resistive, capacitive, inductive energy. And there's a cotton spark test at the end of the day if we don't meet these curves. But generally, we're going to take one of three approaches because we exceed those energies. And so we have to contain the oxygen away from the energy sources. And we can do that if the oxygen stays within a breathing tube and the electronics is somewhere else. The oxygen might get into the electronics box, but we're going to have ventilation to not allow the concentration to exceed 25%. And we'll have an alarm if the fan should fail. Or we can do testing to demonstrate there's no fire. And so these are the design strategies for everything. But we're still going to have oxygen rich somewhere, but we've kept it away. Now, if we're making ventilators, etc., we need to monitor that oxygen. Generally, we want to measure it and know its concentration. So there's at least a sensor in there. And so the sensor needs to make sure it's in an energy limited circuit. And so that is something we try to do. So we keep everything away from the oxygen rich, the breathing path, except the sensor, and then the sensor complies with that safe limit stuff, and then everything else is away from more than 25%, so it's the normal requirements we already talked about. And so typically, with ventilators, oxygen concentrators, oxygen tank, and their breathing paths, accessories, this is all very relevant. And we would take those approaches. We know the sensors are in there, but everything else won't be.